Starting. Okay, so looks like that's about 30 seconds. We'll end the poll. Hopefully you guys can see this. About 30% in civil and infrastructure, 64% in mining. We do have a few trickling in environmental, energy, and a few students. Okay, so the live is working because I just heard myself. And then let's do your experience with CPT. So just find out how many people are, pretty new to CPT, frequent user, a little bit of experience, maybe here to learn more. So we'll give you guys about 30 seconds for that. Okay, so let's share the results. Okay, so we do have some that are quite new, maybe 11%. 42, our biggest one, is a little bit experienced, 22% frequent user of CPT, and 25% more advanced applications. Okay, so without further ado, hopefully you guys saw that, we'll get started. Peter, I will hand this over to you.
Okay, Kelly, thank you for that. Hopefully you can hear me okay. Yeah. What I wanted to do is I wanted to talk about use of CPT in mine tailings. I've been doing quite a lot of work in the last few years on independent review boards for large mining projects. And so I wanted to sort of highlight some of the things I've been seeing and thought it would be useful to share. So here's the outline. I want to talk very briefly about how the geologic history, the depositional history of tailings plays a role. And then we'll talk briefly about the role of soil unit weight, piezometric profile, and then, of course, whether or not you can determine whether or not soils are going to be contractive or dilative at large strains, and then how you estimate in situ state, and then go on to large strain, undrained shear strengths, and then partial drainage effects. And I'll also talk about high stress levels, and I'll show some examples. So as I said, the comments are based on observations during tailings review board projects. So here's a little intro that people who are maybe not familiar with tailings dams. Tailings are a waste product from mining, so they typically extract the ore, which is usually in rock. They crush it down, extract the mineral that they're after, and they're quite often left with a very fine sand, silt-sized material that then is often, and with a lot of water from the process, and then they often hydraulically pump that to a facility and then place it into an impoundment. And the impoundment is often constructed with some sort of embankment. And the embankments can be either constructed using an upstream method, which is the top left-hand corner there. So using the tailings to build the embankment as they climb higher. And so it tends to climb up over the tailings, so upstream construction. Or you can have downstream construction where you build a starter embankment, and then as you raise the facility, you keep raising it downstream as you go higher. And then, of course, there's centerline, which is sort of a modification between the two, which is sort of you raise it along some centerline. And so each of the raises is over the starter dam. And so if the raises are over the tailings, it's upstream. If the raises are over the starter dam, then it's centerline construction. So that's a very brief overview. And of course, lots of different equipment is used to push CPT on mine tailings. Here's a couple of photographs from Context. So you quite often see these track-mounted units that are there, often have the capacity to push about 25 tons. So you can push a long way, up to 100 meters in soft tailings, typically. And then you can get amphibious units that can go out over very soft tailings and also float in water. You can also get very lightweight equipment that can also push 20 tons, but they weigh a lot less and they have to be anchored down. So the two things you often want to think about is what's the capacity of the hydraulics to push. Ideally, you want to push about 20 tons, so you have the ability to go down a long way or into harder material or into the foundation materials. And then you want to think about the reaction force. So you can have a small piece of equipment as long as you anchor it down or weigh it down to get the reaction force. But let me talk a little bit about the importance of depositional history, because as I said, a common way of placing the tailings is with slurry deposition. So you have a lot of water, and then the sands, silts, and clays are in suspension in the water in a slurry, and they're discharged either in spigots or individual points. But what happens is as the tailings are deposited hydraulically, they tend to segregate. The heavier, coarser material tends to drop out first. Finer material tends to flow out all the way maybe to the pond. And so what you tend to do is you tend to see the coarser grain material deposited close to the point of deposition and the finer grain material being further away. And so as the point of deposition moves around, it tends to create an interbedded deposit where you have interbedded sands and silts and clays due to this hydraulic deposition. And also, the sort of density of the tailings is a function of the seepage conditions. And so in this little picture, this is actually from Kennecott Mine when I was flying into Salt Lake City one day. So I was able to look down at the Kennecott Mine in Salt Lake City. And what you tend to find is that when you create a beach above water, so a subaerial depositional environment, so the hydraulic deposition, the water tends to flow downward, and that downward flow tends to create slightly denser tailings. And that's likewise true if you have a tailings deposit that has a relatively high permeable foundation. There tends to be a downward flow, and so that tends to create slightly denser tailings. Of course, the reverse is true, that if you deposit into water subaqueously, then when you're depositing in water and the tailings are settling out in the water, usually the only direction as the tailings consolidate and settle, the water typically has to flow upwards. So this upward flow tends to produce looser tailings. And that's likewise true if you have tailings where you might have a fully lined facility, so there's no downward drainage, the only flow can be upwards, and so they tend to produce extremely loose tailings. So the depositional technique and the depositional history has a big role to play in the resulting tailings that you tend to get. In general, tailings deposited hydraulically tend to be relatively loose, and we'll see that later, that because they're loose, they tend to be contractive, and so they tend to have a lower undrained strength than a drained strength. And so as you'll see later, estimating the undrained strength becomes quite a critical element in a lot of design facilities. So when it comes to soil behavior, we know that soils, like tailings are soils, so they're controlled by effective stresses, and the effective stress is the total stress minus the pore pressure. And so you need to estimate the total stress, and that depends on the soil unit weight, and you need to measure the in situ pore pressure, which on a profile is the piezometric profile. And so to get the correct effective stress, you need to estimate the correct total stress and then measure the in situ pore pressures to get the piezometric profile. And the cone resistance, like soil behavior in general, is influenced by effective stresses. And so we know that the measured tip resistance QC needs to be corrected for penetration pore pressures due to the unequal end area effect of the sleeve being just behind the tip. And that's well established. It's been around for almost 40 years now. So we correct the QC to QT using the measured pore pressure and the net area ratio A. A is typically about 0.8. It's 80% of the area. And then we usually like to normalize the cone resistance to account for the in situ effective stress. So as you go deeper and the effective stresses get higher, the measured tip resistance gets higher, but it doesn't necessarily mean that everything is getting better. So you like to normalize the cone resistance as a function of effective stress. And Professor Roth, in his ranking lecture back in 1984, suggested that the best way to normalize the data was to take the corrected cone resistance, subtract the total overburden pressure, and divide it by the effective overburden pressure to normalize the cone resistance. Now, of course, subsequent to that, ideally, it should be based on mean normal stress. But to determine the mean normal stress, you not only have to know what the vertical effective stress, you've got to know what the in situ K0 condition is, and that's not always known. So if it's normalized by the mean normal stress, it's often written as uppercase Q subscript P, and the uppercase Q is now becoming sort of standardized to meaning normalized parameter. So lowercase q is the measured tip resistance or the corrected tip resistance, and uppercase Q is when it's been normalized. So as I say, K naught is usually not known, but in mine tailings, they're hydraulically deposited. They usually have very little stress history. And so normally K naught is in that range of about 0.5 to 0.7. And there's been various efforts to measure it using self-boring pressure meter. It typically comes out with numbers like that. And that means the mean normal stress is about 70% of the vertical effective stress. So it's actually quite common that we normalize it using vertical effective stress. And it's sort of embedded in the correlations that there is this sort of offset between mean normal stress and vertical effective stress. But keep in mind, ideally, it should be mean normal stress. And in some cases, it would be better to do it that way. But in general, practice uses vertical effective stress. It's easier to use. And most of the time, it's reasonably reliable. Now, to get that effective stress, you have to estimate the total stress. And to do that, you have to estimate the unit weight. Ideally, you want to go out and measure it. But what we find, and I'll illustrate it, is using the correct unit weight is very important, particularly in very soft soils. And that's because this net cone resistance is the cone resistance minus the total overburden. And so when you're in very soft soils, the measured cone resistance can be very small. And so when you subtract the total overburden, now this net cone resistance becomes a very small number and becomes quite sensitive to the actual unit weight you use. This is particularly true in soft soils, organic soils, where the unit weight can be very low. So it's important to get the right unit weight to calculate that net unit pressure. Most tailings, of course, have variable unit weights. They're deposited. So as I mentioned, they'll have variable density, so they'll have variable unit weights. And also some tailings have specific gravities that are higher than the sort of traditional normal value for natural soils. A lot of natural soils have specific gravities of around 2.65. That's sort of the classic number. But some tailings have higher values. For example, iron tailings, it's not unusual to get up around specific gravities of 4 or higher. So you almost double the weight or the unit weight of double the specific gravity of sort of more natural soils. Now, there's several methods that you can use to estimate soil unit weight. Kelly and I, in fact, 14 years ago, suggested a method, and here's the equation for it. And one of the things we tried to do is we tried to make it dimensionless. So we had unit weight divided by the unit weight of water. So it becomes dimensionless because all the parameters in the equation are dimensionless. And we also added at the end this ratio of specific gravities, recognizing that most of our database was natural soils, which had specific gravities around 2.6, but 2.65. But recognizing that if you were in soils that had significantly different specific gravity, then you could modify it based on this ratio. And not all other methods did that, but it's easier to apply that correction to the other methods. And Professor Main had a similar method to estimate soil unit weight. And in fact, if you repurpose his correlation and write it in a similar form or plot it on the soil behavior type chart, in fact, the two are very similar. So the two of us had completely different databases, but yet we came up with very similar ways to estimate unit weight. So both of them give very similar answers. Now, there is a group out of Holland that looked at organic soils and made a correction specifically for very soft organic soils. And of course, in recent years, people have done machine learning techniques to try and estimate unit weights using machine learning, which conceptually is a nicer way to go. The difficulty is that the machine learning is constantly updating itself, and so therefore the correlation in a way is constantly changing with time. And also it's hard to see the equation. There is no equation for it, and so these simple methods still tend to be quite popular. So here's an example. So here's a a cone profile. You've got the tip resistance, and the soil behavior type color coding is put underneath it. This is something that Cone Tech started quite some time ago, and it's a really nice feature. So you can see that the browns tend to be sands, and the blues and greens tend to be silts and clays. So it's a visually very appealing way to look at it. And you can see the friction ratios varying, pore pressure, dissipation test, the equilibrium piezometric profile, which we'll talk about later. And then here on the right, the black line is the estimated unit weight, and the red one is from samples. And this is from a site where every meter they moved over and they pushed samples using these very simple little push-in samplers, which the ones out of Europe are often referred to as Mostap samplers. So they look like a cone, but there's no electronics inside. You push them closed-ended, and when you get to the depth required, you pull back, open up the sampler, and then take a sample over a depth increment. And you can see here they took samples every meter, and the measured unit weights agree quite well with the estimated ones. And because of that, a group in New Zealand suggested and said, well, once we've got the bulk unit weight, and if we know it's saturated below the water table, we could then convert that to water contents and to void ratio and to dry unit weights. And at first I was somewhat skeptical that this wouldn't work that well. And that's partly because, the unit weight estimate's not going to be that perfect. And to go to void ratio from unit weight is a little risky. But over the years, I've been using it, and it's actually quite insightful to get an idea of how the material, like water content or void ratio, will vary with depth. And so it gives you some insight in what the variability is. And here you can see that some of the water contents have been added. It's actually doing a pretty good job on this particular site. And also, it illustrates that when you're dealing with fine tailings, that are silt size or clay size, then we encourage people to say, well, if you're going to take samples, then take water contents. Because if you're below the water table and it's a fine grained material that holds the water, then the water content is a very simple thing to do. And then you can plot water content and you can overlay it over the top of the estimated one from the CPT and get a sense of whether or not the CPT is doing a reasonably good job and whether or not it's giving you a reasonably good picture of the variability. And also, of course, it gives you insight into the void ratio. And you'll see later when we talk about state parameter, et cetera, in the bottom line is it's nice to have an independent evaluation of void ratio. And in fine tailings, you can do this very simply by just taking water contents with these simple push-in samplers that are pushed in using CPT equipment. Also, you can estimate the dry unit weight once you've got all of this. And this is quite helpful because in the mining industry, they usually estimate the dry unit weight of the tailings because they want to estimate that so they can get an idea of the capacity of the facility, how many tons of material can be stored in the facility. So they quite often estimate the dry unit weight. And one of the best ways to do that is from a mass balance, where they do a mass balance calculation, the amount of material going in, stuff coming out, the water that's coming out, the water that's being retained. And over the years, they get a pretty good idea of what that average dry density is, and you can compare that with what the CPT shows. So this actually becomes a nice long-term check on your correlation. And if the number you're getting doesn't quite agree with the cone, one easy way to shift it is just to change the specific gravity to get it to move over to match your measurements in the field. So this actually is quite a useful way to get independent checks on what the consistency of the tailings is like in terms of water content, void ratio, and density. On the right-hand side here is plasticity index. There's been a couple of methods, but this one here is a relatively new one that Nick Ramsey in Australia, and I think Nick may be listening to this from Melbourne. And so you can estimate the plasticity index from the CPT data. What we're tending to find is in sensitive silt-sized tailings, The method tends to slightly over predict the plasticity index. But again, you can see the variability, which is quite insightful. And particularly when people take samples and they'll often quote average values, or they've taken samples and there's a big scatter in the data. And so they're struggling to, what's the mean value, et cetera, and what does it mean? Whereas when you see the profile, if you put samples over it, you begin to get some insights that clearly you've got an interbedded deposit where you've got, say in this case, from 5 meters down to roughly 15 meters, it's mostly sort of a silt-sized tailings with interbedded sands, and that's reflected in the way the PI is bouncing back and forwards from low PI sands to slightly higher PI silt tailings. Now, sometimes you get the question of, well, does it really matter if you get the unit weight slightly wrong? And here's an example, very soft tailings, common, say, out in the pond area of a tailings. So the upper 4 meters is extremely soft tailings, actually not so much a solid, it's more of a slurry. And then you get into the normally consolidated tailings. You can see the tip resistance is increasing linearly with depth. So it's a soft, normally consolidated tailings. And so if you try different unit weights, you can see what a big difference it has. So if you put 20 kilonewtons per cubic meter, that's the red line, and 14 kilonewtons per cubic meter is the blue line. You see a big difference in the normalized cone resistance. So a relatively big difference in the peak undrained strength. And here's the OCR, and you see a really big difference in the OCR. And the blue one is closer to the correct answer because we know it's essentially normally consolidated. So you would expect to get an OCR of about 1, and that unit weight of 14 kilonewtons per cubic meter gives us roughly the right answer. Don't worry too much about the upper 4 meters, and that's because it's a slurry and the unit weight drops even lower. And I was just using a single value all the way. And so it sort of does weird things in that slurry in the upper 4 meters. But at least it's telling you it's a slurry and very soft. Now, of course, when you get into denser materials, and here's a sort of this is a variable tailing. So you can see the normalized cone resistance is up around 80 to 100 in the upper 5 meters, then drops down to a lower value. But in this particular case, you can see that varying the unit weight has less of an effect, but it still has an effect. So you can see OCR and state parameter on the right-hand side. You can see it's still playing a role. There is a difference between the two. So the dark green and the red are the two extremes, and the light green is the variable going down the middle. And later when I show you variability in state parameter, it's useful to keep that variability in mind, that some of that variability could just simply be uncertainty in unit weight. So let's talk about piezometric profile. That was the title of the talk. And so non-hydrostatic piezometric profiles are common in tailings. So I mentioned if you've got a fully lined tailings facility where there's no flow, then of course you would expect to have hydrostatic conditions, and that's what's commonly seen. But in a typically unlined tailings facility, and where you might have the foundation soils have a higher permeability than the tailings, which again is not uncommon, or you might have underdrains underneath. So you're actually promoting downward flow. So you're going to get a piezometric profile that is not hydrostatic, and it's going to be less than hydrostatic typically. And so if you do dissipation tests, you can define that piezometric profile, and you can define the phreatic surface. That's where the piezometric pressure head is 0. And the CPT pore pressures themselves, the measured penetration pore pressures, provide insight into the in situ saturation. And I'll show some examples. So what we know is fine-grained tailings have high air entry values. I'll define that in a minute. And that means that they can remain essentially saturated above the phreatic surface. So you can have small air bubbles. So they're not 100% saturated, but they're close to being fully saturated above the phreatic surface. And then if you've got a rising phreatic surface, so as the tailings facility is built over time and the embankment climbs with time and the thickness of tailings climbs with time, so the phreatic surface is climbing up with time, then you can get small air bubbles below the phreatic surface. So it's not fully saturated below the phreatic surface. I'll show examples. So why do soils remain saturated? So on the right-hand side, you can see this soil water characteristic curves. The upper one is for silty sand. And so the air entry value, which is the point when it begins to lose 100% saturation and begins to decline, that air entry value is typically, a few kPa. And clean sands, it would be 1 or 2 kPa. Silty sands would be like, in this case, 20 kPa. But silt tailings can be an order of magnitude bigger, in this case 150, so it's almost an order of magnitude bigger than the silty sands. So sand tailings, fines content less than 10%, have a very small air entry value, and they tend to desaturate quite quickly. So if you drop the phreatic surface, they tend to desaturate quickly. So the air is able to break into the void spaces and you have continuous air and it desaturates. But silt tailings that have a higher air entry value tend to retain the water in the pore spaces. So the air is unable to break into the void spaces. And so you can have small air bubbles in there, but it still has high degrees of saturation, up around 90% saturation. And researchers have shown is that if you have loose contractive soils that are roughly 90% saturation, they can still behave as if they're fully saturated. Because what happens is when you shear them, they have a tendency to contract. And so the small air bubbles go into solution and they become essentially saturated. Now, for clay tailings or clay soils, where you've got clay minerals, you can have very high air entry values, and they essentially will remain saturated forever. And so they will never desaturate, even if you lower the phreatic surface completely. So silt tailings and clay tailings tend to remain saturated even when the facility is closed and they're draining down. So the phreatic surface may be dropping over time, but these fine tailings can remain saturated. So let's have a look at an example. Here's an example from a site that's been inactive for a few years. So the phreatic surface has been slowly dropping with time. So it's draining down. So you can see a typical interbedded sands and silts tailings, the phreatic surface. So they did dissipations every 2 meters. So that's what these triangles are. And you can see that the extrapolation of the piezometric surface says the phreatic surface is a depth of about 14 meters. And the red line shows the hydrostatic. So you can see the piezometric profile is slightly less than hydrostatic. There's downward flow, and of course it's draining down. But from 14 meters up to 2 meters, you can see that there's large excess penetration pore pressures. And if I actually show an example dissipation, so you can see large excess pore pressures of up around 200 kPa that then dissipate relatively rapidly down to zero, because you're above the phreatic surface, but the soils are essentially saturated. So when you push the cone in, the soil is essentially close to saturated. It's like 90% saturated, small air bubbles. And when you push the cone in, those air bubbles get compressed and pushed into solution. So during cone penetration, the material is behaving as if it's saturated. So you get these large excess pore pressures. But when you stop and do a dissipation, they'll actually dissipate to zero, which would imply that they're above the phreatic surface, but the material is still saturated. And here's a dissipation below the phreatic surface, and similar to the one above, but now it's coming to, in this case, 50 kPa. But it's more than that below the water table, so there's a slight downward flow. So here's an example, similar one, soft tailings interbedded, mostly silt tailings with sand interbeds. And dissipation test done every 3 meters here. And what you see is that when dissipation tests were done, they were all essentially going to zero. And so that means there's vertical gravity drainage. So the flow is going straight down, and so the pressure heads are zero. And so the total head is just the elevation head. And so there's downward flow, significantly less than hydrostatic. And I've drawn what you could call the phreatic surface, but really it's the line that represents where the soils are saturated. So the soils are saturated and there's vertical gravity drainage. And this is particularly important because if you install a piezometer here and then measure the pressure from the piezometer, you can measure zero pressure in the piezometer or zero water in a standpipe piezometer, and you could interpret that these tailings are dry. But of course, when you push the cone in, it says, oh no, they're not dry. They're essentially saturated. They're a fine tailings. They're saturated, but there's vertical gravity drainage downwards. And so here's an example of a dissipation test, and you can see pretty rapid dissipation goes to zero, and all of them essentially do the same. So here's an example where there's a typical rising phreatic surface. So the facility is increasing over time, so the phreatic surface creeps up over time. And so here you can see that they did dissipation tests, and if you extrapolate that, you can determine that the phreatic surface is at about 19.5 meters. But they also measured shear wave velocity and P wave velocity. You can see that the shear wave velocity is roughly constant because it's independent of the effective, well, I shouldn't say the effective, it's independent of the drainage conditions and pore pressure. It's controlled by density and effective stress. But the P wave velocity is very sensitive to saturation. So you can see that below a depth of about 27 meters, it's the standard value of roughly 1,500 meters per second in a fully saturated soil. But above that, it's quite a bit less, which would indicate it's not saturated. But in that zone between 19.5 to 27 meters, it's almost saturated. It's got small air bubbles. Saturation's about 90%. And so here's a plot of P wave velocity against degree of saturation. You can see that degree of saturation is expanded, and you can see that when it's fully saturated, it's about 1,500 meters per second, but very rapidly drops. By the time you're at 95% saturation, it's down close to 500 meters per second. So it's dropped to a third of its value. And so here's a publication where they had some experimental data points, and the solid line is from Biot's theory. So theory says that when you get small air bubbles, it increases the compressibility of the fluid in the void spaces. And so the P wave velocity drops markedly. But, from roughly 85% up to 100%, the material is still going to behave as if it's saturated. It's just not strictly 100% saturated. And so you need to be a little bit cautious using P wave velocity to distinguish where the phreatic surface is, because you can still get near saturated material above that level of where the P wave velocity is 1,500 meters per second. So here's that example I showed you earlier with the vertical gravity drainage. And the question comes is, well, does it affect the interpretation very much if you use hydrostatic pore pressure rather than the correct piezometric profile? And this illustrates what that particular profile looks like. So the red one is assuming it's hydrostatic, and the blue one is the correct vertical gravity drainage. So you can see it has quite a big effect on the normalized cone resistance. And the middle plot is the yield stress ratio, or the OCR ratio. And then the right-hand one is the state parameter. And you can see that in this particular case, which is almost zero piezometric head, and it's relatively soft tailings, it has a significant effect on the interpretation. So the bottom line is that it's important to use the correct in situ pore pressure and effective stresses for CPT interpretation, and of course, subsequent stability analysis. Because when you run your stability analysis, you need to be calculating the correct overburden and the correct vertical effective stresses to run your stability analysis. And here's an example. This was a publication Kelly had at the Tailings and Mine Waste Conference a year ago in 2023. And this is a project, it's actually here in the US, and it's a large 200-meter high tailings dam, and it's upstream construction, and it has strong downward flow. It's got a relatively high permeable foundation. At least the permeability of the foundation soil is higher than that of the tailings. And it had relatively rapid rate of rise, greater than 4 meters per year. And what you can see is that there's a strong downward flow. It's not vertical gravity, so it's not zero. In the upper portion, that light dashed line is 35% of hydrostatic. And then at the bottom, it begins to come down to zero at the foundation. So the water is leaving the tailings, and the foundation material is able to handle that water quite easily and carry it away. So there's zero pressure head at the bottom of the tailings. And what's nice about this plot is that this was 172 meter CPT. The upper 100 meters was direct push, and the lower 72 was wireline CPT. And lots of dissipation tests. So the dissipation tests are the red crosses, and the blue triangles are from in situ piezometers. And you see excellent agreement between the piezometers and the dissipation tests. And you see it here, a significant effect it has. So the strong downward gradient is a positive effect for a structure like this. And in fact, 170 meters down, you're talking about vertical effective stresses that are in the order of 20 atmospheres of pressure. Keep in mind that most case histories of flow liquefaction failures are where the vertical effective stress has been around 2 atmospheres. So when you're getting down to 15 or 20 atmospheres, that's a huge amount of effective confining pressure. And I'll talk a little bit later about what influence that has. And then another thing to keep in mind is stress distribution near the embankment is not simply linearly increasing with depth. So, stress normalization is based on either mean normal stress or vertical effective stress. And the vertical effective stress in the K naught is not uniform near a slope. In fact, the definition of K naught in a sloping ground condition is a little bit more complicated because people tend to think of it's the ratio between the vertical to horizontal effective stress. But when you've got sloping ground, you get rotation of principal stresses. So K naught is not that easy to measure when you're near an embankment. But if you do CPTs near the crest or near the slope, then the stress distribution is strictly not linear. Here it's sort of a visual representation of it. And it can have a significant effect in very soft soils. So for example, if you've got soft clays at depth in the foundation, then if you do CPTs, say at the toe, and you penetrate those soft clays, then you have to keep in mind that the vertical effective stress is not increasing linearly with depth. It's influenced by the nearby embankment, and you need to account for that. So here's an image from that well-known tailings dam failure that I was involved in the panel to review the failure. So it's often referred to as Brumadinho failure. The actual dam was not called Brumadinho. It's eluding me the Portuguese name, but it's often referred to as Brumadinho. And the big thing that came out of this, it was a brittle failure. So within the first 5 seconds, this failure occurred. So a massive slope failure that rapidly moved out. And within 5 minutes, 90% of all the tailings retained had flowed out and unfortunately resulted in a significant number of deaths. So let's talk briefly about brittleness and strength loss. So Bishop in the 1950s has suggested this term brittleness index. I actually prefer to call it strength loss index because his definition was it's the amount of strength loss divided by the peak. And so it's a normalized, so instead of using sensitivity, it's a normalized index of strength loss. So when it's 1, you've lost 100% of the strength. And when it's 0, you're not losing any strength. So it goes from 0 to 1, as opposed to sensitivity going from 1 to infinity. And ICOLD have suggested this diagram to sort of try and illustrate what they call brittleness. I'm suggesting a better term would be strength loss index, because the strength loss index talks about the amount of strength loss, which is what Bishop had suggested. And when we talk about brittleness, we're really saying it's the combination of the amount of strength loss combined with the rate at which it loses its strength. So how much strain is required for it to lose that strength. And in this particular example, you can see that the stress strain curve C begins to get to residual strength out around 25% strain, where sample D lost it in 5% strain. So D is more brittle than C, as is B is less brittle. So C and D have similar strength losses, but they have different brittlenesses. It's a small detail, but it's useful for us to get the terminology correct. Now, critical state soil mechanics is becoming a very popular and a very powerful way to look at soil behavior. And what critical state soil mechanics does, it defines the behavior at large strains when soil reaches a critical state. So it's important to remember that it defines material behavior at large strains. But the behavior at small to intermediate strains is also influenced by fabric and microstructure. So for example, all of the early work done on critical state soil mechanics was done on remolded soil. So like Cam clay, the work was done on remolded kaolinite. And then the early work on sands was done on reconstituted sands. And so, research has shown that you can test either reconstituted or remolded soils to get an excellent definition of critical state or the critical state line. But it can be misleading at small to intermediate strains. And so, people like Atkinson and others have said that you can actually estimate the critical state line, just based on the characteristics of the material, the grain size distribution, the plasticity, etc., all can give you an idea of what the critical state is because it's independent of fabric. It's just a function of the characteristics of the material. But the behavior at small to intermediate strains is controlled by fabric. And so testing undisturbed samples is the preferred way to get greater insight. But of course, the problem there is how do you get undisturbed samples? And, 20 odd years ago, almost 30 years ago, we did the CANLEX project, which stands for the Canadian Liquefaction Experiment in Canada. And what we did is we used ground freezing to get undisturbed samples to actually look at the behavior of soil and get an understanding. And what we showed is that the actual behavior was very sensitive to fabric and microstructure. So identifying microstructure is important since it can influence the behavior of small to medium strains. I won't go into that here. It's another topic. I've talked about it before. So let's look at the critical state soil mechanics framework because it's quite powerful. On the left is a sort of clay-like soils. And the thing about clay-like soils is that they tend to have a normal consolidation line that's parallel to the critical state line. And here you can see, so if you've got a normally consolidated clay and you test it undrained, it tends to contract or the pore pressures increase to critical state. And if you've got an over-consolidated clay, they tend to dilate to critical state, which means the pore pressures tend to go negative and the effective stresses go up. Now, sands don't have a unique normal consolidated line. They can be constituted to a wide range of void ratios, a wide range of relative densities. So each of them has their own consolidation curve. And so you could have a relatively dense sand. At low confining pressure, it would be dilative, but as you consolidate it up to higher and higher confining pressures, of course, the density is getting higher, so the relative density keeps creeping up a little bit, but eventually it's crossing over the critical state line and becomes contractive. And eventually, if you go to very high confining pressure, all of them tend to converge to a limiting consolidation line. And so the numerical model that came out of MIT and others subsequent to that tend to use this limiting consolidation line, similar to the way clays use a normal consolidation line. And so again, loose sands can contract to critical state, dense ones tend to dilate to critical state. So what does that mean? So here, if you simplify it, so Bean and Jeffries, sort of took this approach of a linear critical state line. So if you're loose of critical state, if you tested it drained, it would contract to critical state. If you test it undrained, it moves to the left to critical state. And on the right-hand side, I'm showing a sort of simplified strength diagram. So at a given confining pressure, the drain strength goes all the way up to the strength envelope. And that drain strength ratio is represented by the tangent to the friction angle. But if you tested it undrained, it develops pore pressure. The stress path curves to the left until it gets to the critical state line. And so the undrained strength divided by the confining pressure gives you the undrained strength ratio, which I've shown as that dashed line. And you can see that the undrained strength ratio is significantly less than the tangent of the friction angle. But the next one, if you make the critical state line flatter, the same in situ state, but now you get a lot smaller undrained strength at critical state, you get a much smaller undrained strength ratio. So very loose soils can show this strain softening in response in undrained shear, which is sort of essentially what you saw at Brumadinho. And Bean and Jeffries had suggested using a state parameter, which is the void ratio difference between the current void ratio at a given stress to the one at critical state. But when you're looking at undrained behavior, in many respects, it would be better if you use this stress ratio, the ratio of the stresses at that in situ stress. And they're linked. You can see the equation here. The ratio of the stresses, if it's to the log 10, it's 10 to the power of the state parameter divided by the slope of the critical state line. So this stress ratio is actually a better parameter than the state parameter, or if you are going to use state parameter, ideally should be state parameter divided by the slope of the critical state line. And in fact, this stress ratio, in a way, for sands, it's similar to the stress ratio of OCR for clay. And in fact, when he first suggested the clay and sand model, suggested that this ratio should be used. It's not exactly the ratio I'm showing here, but it's the same basic concept. So this CASM model is becoming quite popular, and it uses this ratio as opposed to directly using state parameter. So what's the motivation between why Bean and Jeffries suggested the state parameter? Well, what we know is that the OCR as a measure of in situ state has long been used to predict the undrained behavior of clays from undrained CPT in clays. So when you push the CPT in clays, it's an undrained penetration, and you can predict the undrained behavior of that clay using models like Shansep and defining the in situ state in terms of OCR. And what we know is when the OCR, or more correctly, the yield stress ratio, if it's less than about 4, then typically soils are contractive. If it's greater than 4, clays tend to be dilative at large strain. Now, the motivation behind developing the state parameter as a measure of in situ state was to predict the undrained behavior from drained CPT. So that was the reason Bean and Jeffries did this. They said, well, when we push the CPT in sands, it's a drain penetration, and we'd really like to predict the undrained behavior. Of course, historically, people did that with relative density. But when I showed you that diagram of the concept behind critical state soil mechanics, it shows that because relatively dense sands at high confining pressure can become contractive. So relative density is not really a very good measure of capturing that. And so state parameter is a much better way to do it. And so Bean and Jeffries had suggested that when the state parameter is greater than about minus 0.05, sands tend to be contractive at large strain. So that minus 0.05 is it's slightly on the dilative side, but it would still be contractive. So why is that? Why did they select minus 0.05? Well, when sands have a state parameter of minus 0.05, they're slightly on the dilative side of critical state. And you can see that the upper diagram shows this critical state line. The initial starting point is slightly on the dilative side, but we know when you load them, they initially tend to contract, and then when they get close to the critical state line, or the phase transformation that Ishihara referred to, they tend to then start to dilate, and then will dilate up to critical state. So they initially contract, and then they dilate up to critical state. That's often why it's difficult to define the critical state line from soils that are slightly dense of critical state, because dilation tends to cause shear banding, and it's hard to actually get to critical state, which is why we typically test samples that are on the very loose side, because they always contract all the way to critical state. But if you look at the stress strain curve, what you see is that if the critical state line is very flat, like it is for sands, then you can see that when they contract, they can sometimes rise to a peak undrained strength and then strain soften a little bit before they strain harden back up to critical state. And so when they're strain softening, in strain controlled tests, you can actually measure that strain hardening up to critical state. But in load controlled conditions, usually the sample starts to fail, and it's unable to actually dilate up to critical state because it's under a constant load, and it fails. And this is what Castro did for his PhD back in '69. He showed that in load control, what he referred to as steady state was not always the same as critical state, because when you have that slightly dilated state, it could fail. So that's part of the reason about why Bean and Jeffries chose that minus 0.05. And it's a good, it's not a unique number. It doesn't apply to all soils. It tends to apply more to sands than it does clays. And it's not a unique number that applies to all sands. So what are the CPT-based methods to estimate in situ state? So the question you're trying to ask yourself is, are tailings contractive at large strains? That's why you want to estimate the state. So there's been a number of different methods. So Bean and Jeffries first suggested it, and then Lewis, Jeffries, and Davis in '92 made sort of a breakthrough, and they said, well, we could make some simple assumptions, and we could actually draw contours of state parameter on the soil behavior type chart for the CPT, and it became just a very powerful way to do a quick estimate. And then, of course, Jeffries and Bean in their books, first one in 2006, and then the updated second edition in 2016, gave sort of more advanced ones, and then Shuttle and Jeffries, and then others have advanced it even further. I did sort of the empirical method in 2010, and I updated in 2021. And then Paul Main said, well, you could also estimate state via the yield stress ratio. So the same logic that yield stress ratio can be linked to state parameter with some assumptions. And so he said you could also get state parameter using his method to get the yield stress ratio. And then Olea and Bray sort of empirically sort of in a way updated my method. And then Alaya et al. Out of Western Australia, they looked at drainage effects and also came up with a sort of a modified method. And all of them have different normalization techniques to account for overburden. And I've got the equations down the bottom. So the simple one that Professor Roth suggested, then the mean normal stress, and then this is the one that tends to be used a lot by Bean and Jeffries, which brings in BQ, which is essentially it's the effective cone resistance divided by the vertical effective stress. And then I had one that was sort of had a variable stress exponent that depended on soil type. And there's been a couple of publications that showed that most of the methods provide reasonably similar values, particularly in young, uncemented sand-like soils. And so a lot of mine tailings, of course, are young. Most of them tend to be uncemented. So most of them give pretty similar results. So here's an example. So the one on the left, this is Lewis et al., the contours that they developed. And that was based on the assumption the slope of the critical state line is roughly 1/10 of the friction ratio. And then here's the contours that I had suggested based on clean sand equivalent. You can see sort of similar general shape of the way it curves down as you go from clean sands into silty sands. And all of these were based on drained CPTs. So both of them were designed for sands and silty sands where the CPT penetration is drained. And then based on the work that Alaya did, which was an extension of the Shuttle and Jeffries work. So Smith said, well, you could use specific calibrations of the CPT using the Norsound model for different drainage conditions. And they suggested these contours that went from drained, partially drained to undrained. Of course, the problem is that the contours in the undrained don't look right. In fact, they're completely inconsistent with the experience of CPT in clays over 50 decades, that those contours seem to be going in the wrong direction. But if you look at the contour for the -0.05, the one shown in red, it's got basically the shape about right. Obviously, there's discontinuities when they went from drained to partially drained, which are not quite right. But you'll see the contours that I use actually are quite similar to that red one. There's often, I quite often see where consultants will try, here's one where they tried 6 different methods and plotting them. Of course, they've chosen a pretty crummy scale. They go from -0.3 to +0.3, so it's squashing the variation. But quite often what you find is that the in situ variability of the deposit is often as big as the differences in the different techniques. But the real question to ask is, what will you do with the state parameter? And of course, the whole premise of why the state parameter was developed was, well, you're going to take the state parameter and predict the large strain critical state undrained strength, because that's the thing it's designed to do. So what are the methods to go directly and say, well, what if we just try and estimate the large strain undrained strength directly? And there's a number of methods. Olson, that starts back in '02, suggested one. Theirs is in the bottom left-hand corner here. It's primarily for sands because It's got normalized cone resistance, but it's not correcting for different fines content, etc. So it's limited only to clean sands. And then Bollinger and Idris, they use clean sand equivalent, but they use fines content to correct for clean sand. So it's a little bit cumbersome. And then there was my method on the right-hand side that also uses clean sand equivalent, but just uses the soil behavior type to essentially account for changing gradational characteristics. And up on the right-hand side is the Jeffries and Bean method based on state parameter. So let's look at that one first. So here's the state parameter approach. They actually had 3 plots, but Reed said, hey, you could plot them all on one diagram. And so you've got 3 different curves of the calculated critical state. And then they suggested these straight lines that were informed by case histories. And the first thing that jumps out, it says, well, case histories don't agree with critical state. And I think that's partly because case histories are more load controlled, whereas critical state is the ultimate state would get to under strain control conditions. But as I showed you, you can have slightly dilative material that wants to strain harden up to critical state, but under load controlled conditions, it's unable to do so. So a lot of the case histories plot to the left of the theoretical critical state because of the load controlled conditions in the field. So, this is nice, but it's difficult to apply and it's inconsistent. So for example, when you've got negative 0.05 state parameter, in theory, state parameters dense of that should all be dilative, but the straight lines just keep on going. And so that doesn't seem to be too logical. And actually a more logical thing to do is what Bean and Jeffrey should have done is they should have normalized it to state parameter divided by the slope of the critical state line. Then you get a single calculated critical state, and then each of the straight lines become these straight lines. And I think what's likely is ideally these straight lines should curve up, because when you get beyond a state parameter of minus 0.05, they should all be heading towards the drain strength. So by curving them up, they're going to the drain strength. So this is what I suggest the relationship should look like. It would be better if it was state parameter divided by the slope of the critical state line. Here's the equation for the actual critical state line, and then each of the dashed lines are informed by case history. So you can see the important role that the slope of the critical state line, and as you'll see later, that slope is not a single value. The critical state line is actually curved, so that slope keeps changing. So you keep changing as you go to higher and higher confining pressures. And you can estimate the slope of the critical state from the CPT. Of course, Pluis had suggested it was the friction ratio divided by 10. And on the left-hand side here, David Reed gave an update. He sort of showed Bean and Jeffrey's data and then some of his own data and said that there was a link between the slope of the critical state line and the soil behavior type index, IC, and Paul Main had suggested simple equation. And so here, the right-hand one's interesting. So Pluis's would just give a vertical line and say, well, the slope of the critical state is that vertical line. Now, that's sort of not very logical, but fortunately, most of the data plots in the middle of the chart. So these curved relationships, which are linked to IC, are a better fit, but it happens that where most of the data is, Pluis's method actually works pretty good, simply because most of the data fits in the middle of the chart. So this is the method I had suggested in my update in 2021. I know it's a bit complicated. I don't have a lot of time to go through it. But based on case histories, I suggested the red line. And of course, it steeply climbs up, because eventually when you get clean sand equivalence greater than 70, you're moving towards dilative material where it's controlled by the drain strength. And also the gray data was the peak undrained strength, but focus on the remolded or the liquefied undrained strength. So I suggested that when IC is less than 3, so it's a drained penetration, and the vertical effective stress is less than 300 kPa, because that's what the case histories were, then this is a reasonable empirical correlation that seems to fit the case histories quite well, and is generally a lower bound to the case histories. But when you have undrained penetration, so when IC is greater than 3, and typically you're into an undrained penetration, then you can just use the sleeve friction directly as a measure of the remolded strength. So the remolded undrained strength ratio is the sleeve friction divided by the vertical effective stress, which happens to work out that it's the friction ratio times the normalized cone resistance divided by 100. Because when IC is greater than 3, the stress exponent is 1, and so that's the way it works out. And so if you plot that on the soil behavior type chart, so here's the updated soil behavior type chart. So here's the contractive dilative boundary, and you see that that actually is quite similar to the one that Smith showed going from drained to undrained. So we're consistent there. And this simplified boundary of a clean sand equivalent of 70, I've curved it over in the clay region to match an OCR of about 4. And so here's the trends. So increasing state, increasing sensitivity moves all the data to the left, increasing yield stress ratio or OCR moves data upwards. And so this is what the contours look like. So if you take the method I showed, so in the drained region, it's that curve. And in the undrained region, it's basically the sleeve friction. And this is what the contours of sleeve friction would look like, divided by vertical effective stress, and then the transition between the two. So it's a useful plot to compare methods. And in fact, if you put the case histories on here, the case histories fit these contours remarkably well. But notice that the case histories show large site variability. It's not just a single data point, it's a big blob of data, because the in situ data generally has a fairly high variability. So let's look at the methods to view the data. So you can look at the yield stress ratio, clean sand equivalent, state parameter, or just look at the undrained strength ratio directly. But because CPT data is a lot of data, it's often collected maybe every 1 centimeter. So you have thousands of data points. So you can actually look at the statistical variation. So you can visually see how it varies here as a function to the contours. But here you can look at the frequency distribution or the cumulative distribution. And often the frequency distribution is log normal. And so often the mean value is often quite similar to the 30th percentile value, for a log normal distribution. So you have enough data to actually look at the statistics of it. And I'll illustrate that later. So let's talk briefly about the role of partial drainage. So in clean sands, we know it's essentially drained. In clays, it's mostly undrained. In silts, it can be partially drained. And we had sort of suggested, along with Jason De Jong and others, that when the time for 50% dissipation was less than about 50 seconds, then partial drainage may influence the results. There's been a lot of research done on normalized penetration resistance, but some of the nicest work was Alea et al. Out of Western Australia presented this rather nice plot. So you've got state parameter on one axis, normalized velocity, and then normalized penetration resistance. And of course, what it nicely showed is that when you've got contractive soils, the undrained cone resistance is smaller than the drain strength. But when you've got dilative soils, the undrained penetration is higher than the drained. So you've got this warped surface as a function of in situ state and penetration rate and normalized cone resistance. And if you look at it just straight on, you can look at it this way. But what's important to note here is a lot of tailings in situ often have state parameters around 0. So somewhere between -0.05 to +0.05. So that's a common number. And you can see that when it's -0.05, partial drainage has no effect. So, it's neutral between dilative and contractive at large strains. And so partial drainage has no effect at all. And the little diagram on the right is just sort of highlighting that when BQ is greater than about 0.2, you're often into undrained penetration. And here's a plot. So Monforte et al., the group out of Barcelona, did some numerical analysis on CPT, and they were looking at rate effects and sensitivity. And they looked at soils that had different sensitivities, from a sensitivity of 1 up to a sensitivity of 4. And they looked at undrained, drained, and partially drained. And what they showed is that depending on the assumed interface friction, the data tended to move diagonally up. And I've added the contours of the liquefied undrained strength ratio using my empirical method. And what you see is that generally partial drainage tends to move the data diagonally up, similar to these contours. so that the effect of partial drainage in very loose materials is relatively small when you're estimating the residual strength, but of course significant if you're trying to estimate the peak strength. So I don't think partial drainage is as big as a problem as people tend to think. Here's an example of a soft tailings. They did dissipations every meter. And if you look at some of the dissipations, they're pretty rapid, typically around 30, 33 seconds. All of them are in that range of 30 to 40 seconds. If we zoom in on an area, so just zoom in on this area, you begin to see where there are some actual sand layers that are there, but there's also these frequent dissipation tests done every 2 meters. And of course, the dissipation tests in a way screw up the drainage because it drains. And then when you start pushing a grain, it takes a little amount of penetration to get back to being an undrained penetration. So what you can do is you can zoom in where you know it's undrained. Here from 13 to 14 meters, there's no dissipation test, no sand layer. And so you can zoom in, it's fully undrained penetration, BQs up around 0.6 or higher. And when you look at that data plotted on the soil behavior type, it tends to plot as a nice little area showing, yes, it's undrained and the material is sensitive, and you can make pretty good estimates of the undrained strength. Once you've identified this is the rain that I know is undrained. You don't need to bother with state parameter really. So I'm running out of time, but I'm quickly going to zip through an example. So this is an example. It's a site in Africa. It's an upstream constructed dam. So it's a ring impoundment. It's about 4.5 kilometers long all the way around. It's classified, consequence classification is very high. So you've got a compacted starter dam over residual soils, and it was upstream constructed using cell construction, and they did CPTs. So here's the normalized CPTs, nicely showing that the tailings are mostly contractive. They're a little bit denser in the sand shells, and they're sandier. And the compacted starter dam, compacted residual soils, they're dilative, and the residual soils are dilative. The tailings have a fairly high fines content, and they're generally a low PI to non-plastic, interbedded sands and silts. And again, there's slightly downward flow. The piezometric profile is about 70% of hydrostatic. So it's not vertical flow, it's slightly inclined flow. So the residual soils are actually quite clay-like, so they have a relatively low permeability. And the water is flowing towards the starter dam and into the foundation. So you get this slight downward flow. And here, this is just an example. If you had installed piezometers and just a single piezometer, you'd estimate the wrong phreatic surface because the downward flow means you would be off a little bit. And the more the flow is downward, the more you would be off in estimating the phreatic surface and how important that can be. And this is just illustrating, the statistics of the data. I showed you that profile earlier. And so when it comes to stability, it sort of says, so what's the risk of instability? So if the factor of safety using residual undrained strength is much less than 1, then, if you think of the stress state, so the in situ stress state is very high relative to its residual strength, so much, much higher. So here's the stress strain curve, a lot of strength loss that can occur. Factor of safety is much less than 1. So the in situ stress is much higher than the residual strength. So it illustrates that the in situ stress is quite close to the yield surface. Here I'm just illustrating the yield surface as a very simple straight line. It's actually a curve, but just illustrating that you have a high risk. So it's easy to trigger because you're close to the yield surface. And if it does trigger, there's significant strength loss. So you're going to have a high potential energy, and that will convert itself to kinetic energy. So there's a high risk you're going to have flow. Now, if you have a less steep slope, so the in situ stress is lower, so the factor of safety using residual strength is closer to 1. Here it's slightly less than 1, but it's a lot closer to 1. So now you can see that the in situ state is a longer way from the yield surface, so it's going to be harder to trigger. And when it does trigger, it's got very low potential energy, so it's much less likely to flow and more likely that it would slump, unless you've got free water. Like if the pond is close to the crest, then the water would add to the problem, and it could flow simply because you're releasing the water, and that would exacerbate the flow. But assuming that there's no pond close to the embankment, then it would be more likely to be a slump. So using the residual undrained strength, calculating the factor of safety, how close is it to 1? The closer it is to 1, the slightly lower the risk is. If it's much less than 1, the higher the risk is. And so here's that example of that upstream constructed. And so there's a tendency in industry that people use a prescriptive approach where they said, well, I have to design to a certain prescribed factor of safety. And so I'll select a single state parameter, I'll select a single residual undrained strength, and I'll calculate the factor of safety. But in reality, when you've got CPT data, you've got this frequency distribution of residual undrained strength. Now, there's uncertainty both in the in situ variability as well as uncertainty in the model. The interpretation is not precise. And so there's some uncertainty here. And so the recommended approach is, at a minimum, do a sensitivity analysis and say, well, why not calculate the factor of safety over this range of values where you've got your frequency distribution from the CPT, so you know what you think is the representative, so you can quote that single value, but at least it gives you a measure of the uncertainty that it could be significantly lower or a little bit higher. And then, of course, if you look at remediation measures, either flattening the slope or adding a buttress, you're going to reduce the risk. So you're essentially going to raise up that factor of safety. And you've still got the level of uncertainty, but you want to raise it such that even with that uncertainty, you're going to feel comfortable with the risk mitigation measures of either the buttress or the flatter slope. So just to finish off, just touch on high confining pressure. So back in 2017, I'd sort of said, well, the critical state line is not a straight line. It's a curve. And the curvature means that as you go to higher and higher confining pressure, the limiting consolidation line becomes roughly parallel to the critical state line. So at high confining pressures, tailing sands tend to look a bit like clays, normally consolidated clays. And here, if you look at the strength loss index as a function of this stress ratio, so although the state parameter is getting looser as you go to higher confining pressure, the ratio is getting smaller. So it's the ratio that controls things because the slope of the critical state line is changing so much. And if you plot that up in terms of what does this minimum undrained strength ratio look as a function of confining pressure, you can see that as confining pressure goes up, this minimum undrained strength goes up as well. And case histories tend to be at low confining pressure. And this was a case history that we published about a tailings dam in Chile that illustrated that at these very high confining pressures. So that example of that 200 meters upstream constructed tailings dam, you've got in situ confining pressures at depth between 10 to 20 atmospheres. So you're up around here, not way down here as you're at low confining pressure. And in that 2017 paper, I suggested that you could use friction ratio as a rough guide of when you would begin to get this more ductile behavior. So I know I've gone a little long and I've moved quickly, but fortunately there is a recording so you can watch it at your leisure and slow me down a little bit more. But in summary, CPT and seismic CPT with pore pressure measurements are the preferred in situ tests to evaluate tailings behavior. And ideally supported by lab testing for high risk. So as the risk gets higher, you want to do more and more lab testing. So for relatively moderate risk projects, you at least want to do index testing, things like how plastic are the materials, because we know that low plastic materials tend to be more brittle than high plastic materials. That was on a previous slide that I forgot to mention. And then you want to maximize the interpretation because after all, seismic CPT, you're getting 7 measurements: tip, sleeve, pore pressure, rate of dissipation, equilibrium pore pressure, shear wave velocity, P wave velocity, and also you can get resistivity. So 7 or 8 measurements in one cost-effective test. And here's all the normalized parameters. So the other thing to do, important to measure the in situ pore pressure and the piezometric profile so that you get the correct in situ effective stress, both to normalize the cone data and for your stability analysis. And then also, if you estimate the unit weight, you can get a good check whether or not that's consistent based on samples, and you can base it both on samples as well as mass balance to see if they are at least consistent, and also based on the specific gravity of the tailings. So the other thing we notice is that fine tailings can be essentially saturated both above and below the phreatic surface, and that if they're loose and contractive, which most of them are, then they'll behave as if they're fully saturated. So just because you get a low P-wave velocity doesn't mean that they're going to be unsaturated and you can use drained parameters. You still need to use undrained parameters. And simple methods to evaluate if tailings are contractive at large strains and to estimate liquefied strength ratios are very helpful. And, do you really need to estimate the state parameter? I see consultants spend a lot of time trying to estimate the state parameter using many different methods. And in the end, it says, well, what did you actually do with this number? In the end, you wanted to estimate the liquefied or the residual undrained strength ratio. And in fine tailings, if the penetration is predominantly undrained, you can do that directly. You don't need to go via state parameter. And then also it's important to evaluate microstructure. So some tailings are lightly bonded, and that can play an important role. And last of all, design should be risk informed. And so the bottom line is if you have a high-risk project where there's potential loss of life, then you should assume that strength loss will be triggered in contractive, saturated, or near saturated tailings at some time in the life of the structure, because the risk is just too high. So, thinking that you can actually estimate the in situ state to a high level of accuracy and then run a numerical analysis to prove that it's not going to be triggered, you have to keep in mind the risk of the project. And if the risk is very high, you often need to err on the conservative side, because if you get it wrong, it could be catastrophic. And so it's better not get it wrong. So here's some reference documents. You got the CPT book. I've got the CPT guide with Kelly, and then Paul Main with ConeTech have their guide as well. And they're quite complementary. Paul is focused more on parameters. I've tended to make mine an overall guide. So they're quite complementary in terms of reading both of them. And they're both free, which is helpful. So I know I've gone a little bit over time, and hopefully we'll have some time to answer questions. Kelly.
Yep, we have quite a few questions. So I'm not sure if you can see some of the open questions. They started, earlier on in the presentation. One of them, a couple go back to the GS values. Are you able to see the questions
If I can get rid of my
pop up,
laser,
or
if I get rid of my laser pointer, I'll be good.
Oh, got it.
Oh, there we go.
Okay.
I
So
finally
the
got it.
first one is, regarding density estimations. If we're working in natural soil, can we use GS as 2.65?
Yes.
Then at the end of the equation,
Yeah.
we would have 1.
Yeah, if you're dealing in natural soils, then a first estimate would be 2.65. It's pretty reasonable. We know it seems to work quite well. It's always useful to know, the higher the risk project, you definitely want to do some lab testing. Of course, basic index testing is a given. And basic index testing means, well, just double check what is the specific gravity of the soil. And you don't need an undisturbed sample. You can just take a very simple push-in sample with CPT sampler to get a small sample, measure the specific gravity, and while you're doing it, also get the bulk unit weight and the moisture content and do Atterberg limits, etc.
Okay, some of these are a little bit longer. Okay, so one of them is comparing dissipation tests with push vibrating wire piezometers. So if the CPT and the piezometer have different readings, what are the considerations and which readings might be considered more reliable? And why in a sandy material or compared to a fine grain material would take a longer time for dissipations with CPTs?
Yeah. The thing to keep in mind is that in coarser tailings and coarser soils, dissipation tests occur quite rapidly. So they're very useful because, in a relatively short period of maybe 5 minutes, you can get to equilibrium quite quickly. And experience has shown that the equilibrium pore pressures from the CPT are exactly the same as in situ piezometers. But of course, the CPT is giving you the in situ pore pressure at that time that you took it. Of course, piezometers can monitor changes in piezometer with time. And so sometimes the difference could be just simply time. Sometimes the difference can be that you're dealing with low permeability material and the CPT doesn't fully get to equilibrium. And so the in situ piezometer, that you can wait several months for it to come to equilibrium and get the true equilibrium pore pressure. So most of the time they agree. Sometimes they can be a little bit off. Sometimes they can be a little bit off, partly because of lack of full saturation. You know, that if you're not fully saturated, you know, like 90% saturation, it can throw off the in situ piezometers.
Okay, what procedure measures would you recommend to interpret CPTs pushed into filtered tailings with very low dynamic pore pressures and zero or near zero equilibrium pore pressures? And then asking about suction
Yeah,
affecting the CPT interpretation.
yeah. Yeah, so filtered tailings, of course, they're different from hydraulically placed. They've often squeezed the excess water out. So they're placed at a lower moisture content, and sometimes they're compacted. So it's a bit like a compacted earth fill. They're not 100% saturated, but the thing to keep in mind is that if you're compacting something to optimum moisture content is often greater than 80% degree of saturation. So they are, in fact, close to being fully saturated. So they'll have some suctions. But what we know is that the suction is a function of grain size. So as we saw, you know, silty materials tend to have relatively low suctions. Clay minerals can have relatively high suctions. But in the end, what we know from experience is that the value of the suction only tends to impact the cone data in the upper 5 meters or so. Once you get below 10 meters, the total overburden pressure often overwhelms the suction. And so the suction doesn't play a great deal. And of course, the deeper you go, the compaction from the overburden pressure is squeezing the voids and tends to make even filtered tailings become more saturated. So at depth, filtered tailings do tend to become saturated. And of course, suctions play a minor role. And so the CPT can be very helpful in terms of determining, so where is the saturated filtered tailings in a filtered tailing stack? They're often referred to as dry stacks, but in reality, they're not dry. They're moist, and often at the bottom, they can be saturated. And the CPT can be very valuable in terms of determining how moist are they and where is the saturation level and how loose are they?
Yeah, a couple questions related to that. So asking about a hypothetical case where CPT passes through a material that indicates Q close to zero. Can we use correlations to determine undrained resistance, peak and residual?
Oh, sorry, say that again?
So if the CPT passes through a
Oh,
material
yeah.
and it's measuring kind of zero pore pressure,
Yeah.
dynamic pore pressures are close to zero, um, they're
Yeah.
asking, can we use correlations to determine undrained resistance? Somebody else asked, can it
Yeah.
be interpreted that the soil is not saturated, which you sort
Yeah.
of
And I
addressed.
must admit, I whizzed through that example pretty quickly, but I showed an example of interbedded tailings. And so what happens is that in the fine silt tailings, the CPT penetration was undrained, BQ up around 0.6. But every time you hit a sand layer, it became drained. And so when you look at the data as a whole and plot it on the soil behavior type, you get a big scatter of data. You know, some of it plotting up towards the drained area in sands, most of it plotting down in the undrained region. And so what you can do is that you obviously cannot predict the undrained peak strength or residual strength directly. Well, you cannot estimate the peak undrained strength in the sandy layers directly because it's a drain penetration. So that's why people use state parameter. But what you can do is, and what I illustrated is you can zoom in on the data and zoom in on where you know it's undrained. And so you can say, I can definitely predict the peak undrained strength and the residual undrained strength from the CPT directly because I know it's undrained in this zone. And so I can sort of remove a lot of the scatter by zooming in on the data where I know it's undrained. And likewise, you can zoom in on the data where you know it's drained. And when you do that, you'll tend to find, yes, it's plotting up in the drained region, and no, you cannot predict the peak undrained strength because it's a drain penetration. So you have to go the alternate route, which is you can either estimate state parameter, or you can just use my method that says, yeah, I can estimate the residual undrained strength empirically once I recognize that it's a drain penetration. That's what those contours try to do.
This one's in the chat, but I think it's relevant. We are planning to potentially do a webinar on CPT and Slick and some of the software programs next year. So somebody's asking, how can you find documentation or training on developing the plots and graphs that you did, especially when there's special formulas that don't come in the software. And I noticed one of the features, and this is our tip, duplicate CPT profiles and then change the values in one of them and use the overlay feature. That's what Peter was showing a lot, overlays, where one thing was changed and one was using something different. So that's sort of a tip.
Yeah, we'll do a webinar on how to do these tips. But Kelly says, if you want to play with variables, what you do is there's a little button that says, just duplicate a CPT and then change one of the variables like unit weight or piezometric profile, and then plot the overlay of those two plots. So it's exactly the same profile. You've just changed one of the variables, and it's a very quick way of seeing, well, how important was that variable? And the program does allow you to input your own correlation. So if you want to try someone else's correlation and see what the effect is, yes, there's a way that you can actually type in your own equations and the program will do it for you.
Okay, next question. Regarding your 2021 correlation to estimate a large strain ratio strength, would you recommend to use the correlation for ICs greater than 3.0 based on friction ratio, even in tailings with low T50 values and partially drained conditions?
Yeah. And experience is showing that when you get into these silt tailings that plot low down on the chart with IC greater than 3, yes, it's quite common that you get these T50s of around 30 seconds or so, which would indicate partial drainage is a problem. But when you look at things like the BQ value, it says, no, clearly this is predominantly undrained. So, although the T50 is relatively rapid, it still is essentially an undrained penetration, and it works just fine. And also I illustrated that that numerical work and supported by experimental work shows that when you're estimating residual undrained strength ratio, partial drainage doesn't seem to play a major role.
Okay, you touched on this quickly at the end, but this one's asking about like oil sands, tailings dikes with a depth of 50 meters. Are the equations still valid for the deeper sections where they have higher effective stresses exceeding 300 kPa?
Yeah, and I whizzed by it again quickly, but that case history from Chile, where we looked at the effect of high overburden, what was really surprising is the CPT actually did a pretty good job adjusting for the very high overburden pressures. Is that as those overburden pressures got up to very high numbers, the CPT interpretation did appear to be correctly tracking it, which for me was a pleasant surprise to say that, the normalization does seem to work. And of course, theory says it should work. Critical state soil mechanics, Professor Roth, when he first said, hey, you've got to normalize the data, it does basically work. And when he suggested that, I was living in Italy at the time, and Professor Yamlakowski was doing a project in Bologna where he was doing a 300-meter deep borehole with wireline CPT to investigate settlement from pumping. And when you encountered these clays at great depth, when you normalized it, they all normalized to the same point. So it says, normalization works surprisingly well.
So this one's a little bit on rate effect, asking about pushing the CPT at maybe 10 centimeters a second instead of the standard 2 in tailings. Should you change the push rate for different types of tailings?
So when I did my PhD, which was 44 years ago, we played around with rate effects and very quickly realized that when you're playing around with rate effects, permeability varies by orders of magnitude. So you have to change the rate by orders of magnitude. And very quickly you realize that 2 centimeters a second is the standard rate. If you go 10 times faster, it's a scary fast rate. And if you go 10 times slower or 100 times slower, it's a ridiculously slow rate. And so it takes you hours to push a half a meter when you go 100 times slower. So it just doesn't become practical. Now, people have suggested we could do twitch tests where you do a little bit at different rates. But what I tried to show you is that for a lot of the soils we're dealing with, particularly tailings, where the in situ state is not super loose, it turns out that rate effects typically don't affect the results that much, other than peak strength. If you want to estimate the peak strength, it has an effect, but residual strength, it has a much less effect. And the bottom line is, why do you want to estimate the peak strength? Peak strength doesn't really play much of a role in stability because there are many ways in which you could trigger strength loss in loose contractive materials. You don't have to go through the peak strength. The only thing the peak strength might be useful for is just to give you an idea of how close you are to yield. So if you use the peak undrained strength and you get a factor of safety close to 1, it basically says you're very close to yield.
This is just a question regarding G naught. Is there any evidence of G naught or G max anisotropy in tailings? Sorry.
I can't remember them. You've got me saying it wrong.
Yeah.
No, there's very little evidence. Generally, for most natural soils, there's about a 10% anisotropy. That's how you say it.
Oh, yeah.
There's about a 10% anisotropy, which is relatively small. There are cases in these very old clays in the UK, like millions of year old, where they're getting bigger values. Like instead of 10%, they're getting like more than 50%. But those are very old soils that have microstructure. And so that becomes a separate issue. But for most natural soils that have little or no microstructure, anisotropy is very small, and we typically don't worry about it.
Okay, 2 questions about SU value at 30th percentile. So one of them kind of asking, is it only limited to the 30th percentile? The other one basically asking what value of the liquefied shear strength would you recommend to take for sand-like soils? It's recommended 30th percentile for clay-like. What would you say?
Yeah, there's been quite a lot of research in terms of variability and that failures tend to occur through the weaker areas. And so there's been this tendency that the mean value is not necessarily the right value to choose. You should use a value lower than that. And so numbers that have been suggested have been like somewhere between 20 to 30%. And as I showed you, when you look at tailings and you look at residual undrained strength, the frequency distribution is usually log normal. It's not a normal distribution. And so when it's log normal, it actually works out that the peak of the log normal is often close to the 30th percentile. So the two become quite consistent to say, yeah, the 30th percentile seems to be a reasonable value to use. And so if you're going to use a single value, that's industry practice has generally homed in on something like the 30th percentile as being a reasonable representative value.
And there were a couple of things in the chat sort of talking about sleeve resistance and someone asking, about I guess the accuracy with the sleeve. So this one, someone's asking, does that mean getting large strain strength from sleeve resistance? Is that an underestimation of the large strain strength?
Yeah, lots of research. Paul Main has done quite some nice work on comparing sleeve friction values with residual strength and showing that the two agree quite well. The only time they tend to disagree is when sensitivity gets very high. So when sensitivity starts to exceed 15, like these very sensitive clays, then of course the residual strength gets down to very low numbers. So usually when you're getting to that high sensitivity, you've got liquid limits, sorry, water contents much higher than the liquid limit. And so that means you've got residual undrained strengths less than 1 kPa. And so the ability to measure sleeve frictions down to 1 kPa becomes quite limited. And so you're not going to get it perfectly accurately, but at least it's going to tell you, hey, it's a very small number. And modern cones are much better designed than they used to be. A lot of cones are compression cones where it's a separate load cell and they've got equal end area friction sleeves, and most contractors take careful procedure on zero load readings and cleaning the cone, cleaning the O-rings, etc. So the sleeve frictions are in fact remarkably good. Now, if you're in very soft materials and you're dealing with very low residual undrained strength, then quite often people will go to lower capacity cones. So that lower capacity cones have higher accuracy. And so if you want to check the accuracy, you can try 1 or 2 soundings with a low capacity cone to see if there's any significant difference. But generally the cone is a screening technique which is going to warn you and say, hey, these sleeve frictions are really low, which is warning you to say, yeah, the residual undrained strength is going to be a very low number. Check the water content. If the water content is higher than the liquid limit, then yes, you should expect to get these low numbers.
Okay, someone is asking, what is the most appropriate approach to account for the fabric effect in remolded samples, ensuring an accurate assessment of the state parameter and its evolution throughout the test?
Yeah, the bottom line is very difficult. And that's why I say state parameter and critical state is very useful to understand the behavior at large strains because it's independent of fabric and microstructure. But when you're dealing with intermediate strains, so if you want to do numerical analysis and you're trying to determine whether or not something's going to be triggered, then it becomes very sensitive to fabric and microstructure. You know, we've suggested that you can estimate microstructure by measuring the shear wave velocity with the CPT, but fabric is much more complicated, and it's hard to know whether or not your sample in the lab is duplicating the fabric in the field. That's a whole area of research that still has not progressed very far, and it's still a bit of a warning sign. And of course, there's lots of research saying, hey, when I make reconstituted samples different ways, I get different results. You know, I get the same critical state line, but I get different stress strain curves. And it says, yeah, the fabric plays a role. And it's hard to know exactly what the in situ fabric is like, other than trying to make your sample as close to the way it was placed in the field as possible. You know, hydraulically with certain drainage conditions, etc., that where you try to duplicate it. And research out of Western Australia has suggested, you know, hydraulic depositional, I think they use vibration to get the correct in situ vibration. So hydraulically with vibration to get the correct void ratio shows promise in getting probably a better handle on the fabric, but we still don't know.
Okay, last one, kind of going back to the percentile. So someone wants to define exactly what percentile to use between 20 or 30 of your explanation, sort of about the distribution.
Yeah.
Or is
Yeah.
it kind of only a standard choice?
Yeah. And the answer, hopefully, I tried to make it clear right at the end, is don't use a single value. You know, the cone is going to give you a frequency distribution and run a sensitivity analysis covering the full range and then see what the result looks like over that range. And so move away from a prescriptive approach and go more towards a risk-informed approach that says, look, I don't know exactly what the value is. I think that the representative value is roughly in this range. And so what are the factors of safety in that range? So move away from a single value and start to look at a sensitivity in terms of the range. And so move towards a risk informed. Of course, in the long term, we could go to a full probabilistic. And so if you really had a well-defined geometry and you had lots of cone data, you could do a probabilistic stability analysis and actually see what the likelihood is, the probability is.
Okay, last question, just to throw one slightly out of the tailings realm
Yeah.
here. Someone asking about, have you seen a case where liquefaction potential exceeded 15 meters or 50 feet for natural soils,
Yeah.
not related to tailings?
Yeah. And of course, what that question is really talking about cyclic liquefaction. And what we've been talking about is flow liquefaction for embankments, you know, where you've got a high static shear stress, loose deposits, a low residual strength, so you can get flow liquefaction. What that person's talking about is cyclic liquefaction, which is level ground conditions. And we know from case histories that most of the damage generally occurs in the upper 10 to 15 meters, because as you go deeper, you may in fact develop excess pore pressures, but those excess pore pressures aren't going to do anything because it's level ground conditions. We're talking about sloping ground where earthquakes could trigger strength loss and flow liquefaction.
Yeah,
That's a good
and
one to end on.
also, and on the cyclic one, probably also depending on layering
Yeah, yeah,
of soils and
yeah,
if the
that's right. Yeah,
pressures dissipate.
exactly.
So lots
Good
of
point,
things.
Kelly.
That's probably a different webinar.
Yeah,
But
good
thank you
point.
everybody for being on here. Again, this is on YouTube if you'd like to rewatch it or share, and the link to the recording will be sent out 24 hours from now. And you can reach out to us